can't see it, but I just used almost all 7 parts of the electromagnetic spectrum in the 10 minutes that it took for me to get ready. Wait, what is the electromagnetic spectrum?
Sophia the science gal. Sophia the science gal. Sophia the science gal. Science rules. Sophia the science gal.
Inertia is a property of matter.
Sophia the science gal. Sophia the science gal.
So what exactly is the electromagnetic spectrum? The electromagnetic spectrum is divided into 7 different types of electromagnetic waves: radio waves, microwaves, infrared waves, visible light waves, ultraviolet waves, X-rays, and gamma rays. All of these waves are a form of light, but the only portion we can see is visible light. What sets each of these waves apart is their differences in wavelength and frequency. Wavelength is defined by NASA as the distance between one peak or crest of a wave of light, heat, or other energy, and the next peak or crest of another wave. The shorter the wavelength, the greater the energy, and vice versa. Radio waves with a wavelength the size of buildings have the least energy, while gamma rays with a wavelength the size of the nucleus of an atom have the most energy. Frequency is defined as the rate at which waves occur, measured in cycles per second, or hertz. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So as we move from left to right on the electromagnetic spectrum, the frequency and energy of the waves increases while the wavelength decreases. So now that you know the general background information, let's dive into what makes up the electromagnetic spectrum. As I said before, radio waves have the longest wavelength out of the entire electromagnetic spectrum. Their wavelength ranges from the size of a football to the size of a football field. These differences in wavelength are the difference between AM radio, TV signals, and FM radio. The frequency of radio waves is between 3 Hz and 300 gigahertz. Radio waves have been used to broadcast information ever since the first radio news broadcast in 1920. Today, these radio waves are also used to carry signals for your television and your phone. But how exactly do we broadcast and receive these signals? Radio waves maintain their frequency and amplitude at all times. As I said before, frequency is defined as the rate at which waves occur. Amplitude is defined as the height of these radio waves. Because radio waves will maintain their frequency and amplitude, certain patterns can be embedded in the waves through variations in frequency or amplitude. AM stands for amplitude modulation, as in AM radio. Data is embedded in AM radio waves by changing the amplitude but maintaining the frequency. Similarly, FM stands for frequency modulation and uses differences in frequency to send information. These waves are then received by antennas in radios, cell phones, and televisions. These antennas are able to isolate specific frequencies and convert them into information. Wow! Microwaves have a wavelength between 1 meter and 1 millimeter. Their frequency ranges from 300 megahertz to 300 gigahertz. I think we all know the first thing that comes to mind when I say the word microwave. A microwave! True to its name, microwave ovens use microwaves to heat food. The wavelengths of these waves is about 1 foot. The microwaves used in a microwave oven are set at a specific frequency that agitates the water molecules in food. Soon, the molecules start to vibrate at the atomic level, creating heat. Because the microwaves used only target water molecules, just the food is cooked, not the plate that the food is on. Microwaves have many other uses, including Wi-Fi. They can also be used in weather radar, GPS tracking, and the transmission of phone calls and computer data over long distances. Their ability to pass through rain, snow, clouds, and other obstacles makes them especially efficient in these tasks. The wavelength of infrared light waves ranges from the size of a pinhead to the size of a cell. The wavelengths just get shorter and shorter, huh?
The frequency of infrared waves ranges from 300 gigahertz to 400 terahertz.
The longer infrared waves are the thermal energy we experience from sunlight, fire, and everything more. Objects at room temperature or above will emit infrared radiation. But get this, cold things like ice cubes emit infrared waves too. Special cameras can detect infrared waves and assign false colors to each temperature to create an image our eyes can interpret. Take for example this picture of a parrot. An infrared or heat vision camera can show us where the most heat comes from. But not all infrared waves are associated with heat. The shorter infrared waves are used by remote controls, like this one, to turn off my TV. Visible light. Finally, an electromagnetic wave we can see. Visible light waves have a wavelength between 750 nanometers to 390 nanometers. A nanometer is 1 billionth of a meter. That means visible light waves have a wavelength about the size of bacteria. They have a frequency ranging between 400 terahertz to 770 terahertz. The visible light we can see makes up a mere 1.5% of the electromagnetic spectrum. We see visible light as colors of the rainbow. Each color has a slightly different wavelength, as demonstrated in this picture. Red has the longest wavelength, and violet has the shortest. As many of you may know, all of these colors together produce white light. The opposite works as well. When white light is passed through a prism, it separates into the colors of the rainbow. The sun is the main source of our light, but there are other stars in the universe giving off light too. The color of these stars can tell scientists about their temperature. As an object grows hotter, it radiates light with shorter and shorter wavelengths, therefore changing color. For example, our sun, with a surface temperature of 5,600 degrees Celsius, radiates mainly red, orange, and yellow light. Referring back to the previous picture, these wavelengths of light are longer than the light near the blue and purple end of the spectrum. Therefore, stars that radiate blue light must be hotter than our sun, right? Right! This star, called Rigel, clearly radiates blue light, and its temperature is nearly 12,000 degrees Celsius, more than twice the temperature of our sun. We see because of special cells in our eyes called cones that detect light waves, allowing us to see color. Cones, along with rods which detect motion, make up our retina. Now, as I said before, most everyday objects do not give off light. Instead, drumroll please, they reflect it. Take for example these lemons. These lemons are not giving off yellow light, they are reflecting it. When light hits the lemon, all colors of light are absorbed, except for yellow. Yellow is reflected back off of the lemon, and this is the color that we see. The answer to that, my friend, is held deep in the atoms that make up the surface of the lemon. The color reflected off of the lemon is determined by the arrangement of electrons in the atoms that make up the lemon. These electrons will either absorb or re-emit photons of light with certain wavelengths. This means that for a lemon, these electrons absorb photons of red, orange, green, blue, indigo, and violet light, but not yellow. The yellow light is reflected back to our eyes, causing the lemon to appear yellow. And that is how visible light waves allow us to see. Ultraviolet waves, the next shortest wavelength. Back to the electromagnetic waves we can't see, huh? But some creatures actually can see ultraviolet waves, like bumblebees. Anyways, ultraviolet waves have a wavelength from 400 nanometers to 10 nanometers, about the size of a molecule. Their frequency ranges from 750 terahertz to 30 petahertz. The sun is a major source of ultraviolet radiation, in addition to visible light and infrared. However, younger stars glow much more strongly in ultraviolet light. Scientists classify ultraviolet radiation into 3 categories: UVA, UVB, and, yep, you guessed it, UVC. UVA radiation has the longest wavelengths of the 3. This type of radiation is able to penetrate the Earth's atmosphere. Overexposure to these waves can cause skin conditions. However, UVA radiation is not nearly as harmful as UVB and UVC. UVB radiation has a slightly shorter wavelength. These waves can penetrate the Earth's atmosphere, but it is unlikely. About 95% of these waves are absorbed by ozone in the Earth's atmosphere. We'll get back to ozone in a second. Like UVA radiation, UVB radiation can cause sunburn and serious skin conditions, and even increase the risk of DNA and cellular damage. UVC radiation with the shortest wavelength is also the most harmful. Luckily, almost all of these rays are entirely absorbed by Earth's atmosphere. Whew! What's that? Oh, right, I mentioned ozone. For many of you, the word ozone brings to mind the ozone hole. But what even is the ozone hole? And why is it so important? First, you have to understand the ozone layer. The ozone layer is a layer of ozone, O3, which absorbs harmful ultraviolet radiation from the sun, and is therefore very important to all life on Earth. However, harmful chemicals from industrialization and the pollution that resulted are hanging out in the upper atmosphere. Chemical processes involving these pollutants have caused the amount of ozone to decrease in areas of the atmosphere over Antarctica and parts of South America. These areas are exposed to an unhealthy amount of very strong ultraviolet waves. But ultraviolet radiation isn't all bad. In fact, a healthy amount of exposure to these waves is beneficial because it causes our bodies to produce vitamin D. In addition, many hospitals use UV lamps that emit ultraviolet waves to sterilize equipment. X-rays have a wavelength ranging from 10 nanometers to 0.01 nanometers, about the size of a single atom. Their frequency ranges from 30 petahertz to 30 exahertz. Similar to microwaves, X-rays have something named after them that can often cause a little confusion. When I say X-rays, I'm referring to the form of electromagnetic radiation. This is not the same as an X-ray machine, which uses these X-rays to create X-ray images. X-rays were discovered by German physicist Wilhelm Conrad Röntgen in 1895. He then discovered that by sending these X-rays through a part of the body with an X-ray sensitive film on the other side, you would receive a detailed image of the bones inside. He tested this on his wife's hand. This was the first X-ray image. If you've ever gotten an X-ray before, you may recall signs like this. That's because X-rays, along with gamma rays, are a form of ionizing radiation. Ionizing radiation is a form of radiation in which the energy of the ray or particle is so great that it can remove electrons from the orbit of an atom, forming an ion. Ionized atoms in living cells will either repair themselves, die, or mutate, possibly into cancer. These last 2 possibilities prove why ionizing radiation is so dangerous. But don't freak out the next time your doctor says you need an X-ray. The health risk from X-rays is very low. The use of X-rays to examine injured bones and detect diseases like cancer is very important to modern medicine. Although X-rays have been linked to cancer, a little exposure to them every once in a while is a-okay. Finally, we're here. Gamma rays! Gamma rays have a wavelength less than 0.02 nanometers, about the size of the nucleus of an atom. Their frequency is greater than 15 exahertz. Gamma rays have the shortest wavelength but the most energy. In fact, gamma rays are so powerful that they release more energy in 10 seconds than our sun ever will in 10 billion years. These powerful waves are only produced by the hottest and most energetic objects in the universe, like neutron stars, pulsars, and supernova explosions. On Earth, these gamma rays are experienced in lightning strikes, radioactive decay, and nuclear explosions. When a nuclear explosion occurs, gamma rays are emitted because of the high energy reaction taking place. As I said before, gamma rays are a form of ionizing radiation. But because gamma rays are so much more powerful than X-rays and are in great abundance during a nuclear explosion, people nearby are exposed to an unhealthy amount of ionizing radiation, causing many of their cells to die or mutate, leading to an incurable and fatal disease called radiation sickness. However, gamma rays can be used for good too. In the medical field, gamma rays are used to kill cancerous cells. They are also used in space to detect high-energy objects like solar flares, supernova, neutron stars, black holes, and active galaxies. But detecting gamma rays isn't as easy as it is with other types of electromagnetic radiation. Gamma rays cannot be reflected by mirrors because they are so small they pass through the spaces between atoms. Instead, we can track their collisions with electrons as they pass through a surface. These gamma ray detectors must also be outside of Earth's atmosphere because the atmosphere absorbs nearly all gamma rays. So now that you understand each individual part of the electromagnetic spectrum, let's go back to this morning and see it all over again. When I turned on my lamp, I used visible light to help me wake up. While picking out my outfit, I also used visible light to help me decide which color I wanted to wear. My toaster oven used infrared waves, or heat, to toast my toast. Microwaves were used by my microwave oven to heat up my breakfast sausages. When I was on my phone during breakfast, radio waves were being used by my phone to receive information. Here, the remote control used infrared waves to turn on the television. The weather forecast I saw on my TV was the result of microwaves used in weather radar. Radio waves were also used to receive the TV signals. Lastly, when I stepped outside, I squinted because of the strong ultraviolet waves being emitted by the sun. So there you have it, the entire electromagnetic spectrum in all of its glory. Who knew that invisible wavelengths of light could have such an impact on our lives? It's mind-blowing, isn't it?